The Platonic solids are 5 polyhedrons with special properties, named after the Greek philosopher Plato. The faces of the Platonic solids are congruent regular polygons, all meeting in the same way around each vertex. The Platonic solids are isohedral, or face-transitive, meaning that they are made up of only one type of polygon each. They are isogonal, or vertex-transitive, meaning that each of their vertices are the same. And they are isotoxal, or edge-transitive, meaning that their edges are the same. They are also convex. Using these restrictions, you will find that there are 5, and only 5 shapes like this in 3 dimensions. Euclid proved this fact in his work, The Elements. Other Greeks in ancient times were fascinated by these shapes. Pythagoras knew some of them, and later Plato wrote about them. He associated each perfect solid with the 5 elements. And other Greeks wrote about them. Much later, the German astronomer Johannes Kepler closely studied these shapes, attempting to create a model of the planetary orbits. Obviously, his models based on the Platonic solids turned out to be wrong, but he discovered some other important polyhedra in his studies. Each Platonic solid is named for the amount of faces it has using classical Greek. So the first is the tetrahedron, tetra meaning 4, the cube from the Greek for dice, or also known as the hexahedron, hexa meaning 6, the octahedron, octa meaning 8, as in octopus. Next we have the icosahedron, icosa meaning 20, and the dodecahedron, do meaning 2, deca meaning 10, together dodeca for 12. There's an equation known as Euler's formula that states that for any convex polyhedron, you can add the amount of faces plus the amount of vertices, and then subtract the number of edges, and you always get 2. So in other words, f plus v minus e equals 2. Let's try it out. So we have 4 triangular faces, 4 vertices, 6 edges. 4 plus 4 is 8, minus 6 is 2. We have 8 triangular faces, 6 vertices, 12 edges. 8 plus 6 minus 12 equals 2. And this is true for all of the polyhedra. Using these numbers, we discover an interesting relationship between these shapes. First, let me explain the concept of duality. Let's take a square, the face of a cube, and put a dot in the center. Here's a vertex first view. You connect the dots and you get an equilateral triangle. So now looking at the cube as a whole, let's see what happens when you connect all the dots together. And there, they become the 6 vertices of the octahedron. So therefore it's said that the cube and the octahedron are duals of each other. And we can apply the same method to the octahedron, put the dots, connect it, you get a square, connect all the dots together, and we get a cube. And this is true of all the shapes. So next let's try the icosahedron. Put the dots at the center of each face, connect the dots. First we get a regular pentagon, connect them all together, and we get the dodecahedron. And in the same way, the icosahedron and the dodecahedron are duals of each other. Now we have the tetrahedron left. Using our handy-dandy little trick, we reveal one of the great secrets of the universe. As you can see, the tetrahedron is the dual of the tetrahedron, so it's self-dual. And that's pretty cool. Looking back at the numbers for a minute, we see each dual shares the same amount of edges, but the number of faces and vertices are swapped. For the tetrahedron, the number of faces and vertices are the same, so therefore it's self-dual. That's pretty cool. Every polyhedron has a dual as well as other polytopes in other dimensions, such as tesseracts and tessellations. But back to the Platonic solids, you may be wondering what are some of the more practical applications of all this and how it relates to the real world. Well, if you look hard enough, you'll find them all over the place. For example, the art of M.C. Escher, Salvador Dali, Leonardo da Vinci, and others. You'll find them in minerals and crystals, molecules, life forms even, viruses, boxes, playground equipment, architecture, the list goes on. Dice, D&D dice, and even The Simpsons. Also, you can use your ears to locate some of these shapes. Here's a song that I heard that mentions dodecahedrons.
The square root of a negative number, it was a very good year. It was a very good year for dodecahedrons in a state of quantum uncertainty. We would have sexual intercourse, while at the same time we would not have sexual intercourse. When I was the square root of a negative number.
So in conclusion, the Platonic solids are extremely symmetrical polyhedrons that have many interesting interrelationships. They are very beautiful and important to history, and they have what some would even call a cosmic significance. But there are many other types of polyhedrons and even other polytopes of higher dimensions and stuff to explore. So go check them out and stick around for more on the amazing world of geometry. And remember, respect the dodec. Take care.